with that power cannot be created nor destroyed, only converted, with the exception of nuclear power. He didn't have nuclear power back there. He was short-sighted on the whole thing. So, but anyway, so that means that this is very important for antennas. It means that all electrical energy must be converted in one of three ways: light, heat, or radiation. Those are only three choices. So you have an incandescent light bulb. An incandescent light bulb emits photon energy, light. It also gets extremely hot when you touch it, thermal energy. And it also has some radiation off of it. So, and by radiation, we're talking about electromagnetic radiation. We're not talking about alpha, beta, and gamma radiation. So those are our three choices. On an antenna is just a piece of wire. It's just a piece of wire. That's all an antenna is a piece of wire. Nothing else about it. I know because I went to school, I have an electrical engineering degree, and actually did some antenna design. Super duper cool stuff, and it doesn't pay diddly. So I decided I probably should do something else. And so I started fixing wireless networks, and it seems to have worked out pretty good for a dumb redneck. I've done pretty good. Okay, so here's my question to you. You have antennas, like this Yagi antenna. We'll go over why it's a Yagi antenna, but this Yagi antenna has a piece of wire. It's this one right here. This is the only wire right here that comes off of the radiating element that we plug into our transmitting unit. And this is just a piece of wire. This is like a, I don't know, we'll make up a number because I'm mostly blind. This is like a 9 dB. Now, let's not worry about the dB yet. 9 dB means it has a lot of gain. A lot of gain. So tell me how a piece of wire can have gain. And let me tell you what I mean by that. If I put 1 watt of energy coming in here, and this is a 9 dB, that means that I would have 2, 4, 8 watts of energy coming out of this antenna. 8 watts. I put 1 watt in, I got 8 watts out. How can a piece of wire have a gain? I put 1 watt in, I get 8 watts out.
Self-inductance.
But if that was true, I'd wire my entire house like that, and I would only need a milliwatt to power my entire house. Right? Once again, power can't be created nor destroyed, only converted. Right? The laws of perpetual motion play into fact on everything. Thermodynamics cannot be cheated. So how can I put 1 watt in and get 8 watts out? That's the question. It's a pretty good question, isn't it? Well, here's this trick on it. It's a lie. 1 watt in, it's less than 1 watt out. However, I make it directional. I make it effective radiated energy. This is a Yagi. You see how it points in this direction? My radiated energy is this direction. I have nothing back here. That's what it's doing. It's taking all of that energy and focusing it. And that's what antennas do. They put energy out onto the air, and then the higher the gain, the higher the focus. So here's what we're going to do to think about that. Think of a light bulb, because as George talked about earlier, light is electromagnetic radiation, and it happens to be in the visible range. A light bulb is the exact same thing as our antenna is on 2.4 gigahertz, 5 gigahertz, and yes, it's gigahertz. If you look it up, the G is supposed to be pronounced as in giant. But here in America, we're Americans, so we pronounce it gigahertz, because by golly, nobody can tell us what to do. It should be gigahertz. Okay? Back to where we're at here. So our antennas are the same, they're just at a different frequency we can't see. So think about a light bulb. Think about your nice little light bulb right here. And he radiates energy out like this, doesn't he? He does it in 360 degrees. All the way around that incandescent light bulb. He doesn't radiate off the bottom where you screwed him into the lamp post or the socket down here, does he? And most of them have some kind of reflective material up here on the top, don't they? So that they don't radiate off the top. That's the same thing with an antenna. It's the same thing with an omni antenna. This is an omni antenna right here. Remember, this is the ugliest omni antenna you could ever see. This is a Cisco one, so. It doesn't radiate off the top. It doesn't radiate off the bottom. It only radiates broadside, like a donut, or like a bagel. Or like a balloon. You take a balloon, perfectly round balloon, and you take your fingers, and you put one finger on the top, one finger on the bottom, and push them down. That's a dipole antenna. That's an omni antenna. Creates that donut going. which is also another reason why we run into problems, because people will take access points and mount them up on the ceiling right here, here's my antennas, and put my desk right here, right underneath it, where it doesn't radiate any energy. And they're like, I can't get any closer to this access point, I still can't connect. Because there's no energy coming off that. If they went like this, now they connect. Okay? So this is going to be the key. This is the key. This is how you get George's Google glasses to see RF energy. You see a light bulb. Now how do we take a 100-watt light bulb and make it brighter? For example, this guy right here, this is only a 10-watt light bulb inside here, 10 watt. I turn it on and you stand in front of here, you get black dots in front of your eyes for free. It's only 10 watts. How can it be so bright?
It's all focused in one direction, right?
All focused in one direction. This is a very directional antenna. Very directional antenna. So I take this, I put a reflector behind it, and I put a director on the front of it, just like a mag light. I take a mag light and I can point it, I can adjust the front of the mag light, right, to take the beam of the light and change it. That's what antennas do to RF. Because it's the same material. It just happens to be a different frequency. Okay? Now how about you go out in your backyard where you have a pool. If you don't have a pool, you go out to the Wyndham where you have a pool. If you take a flashlight and shoot it down onto the pool, you get light to bounce off of it, don't you? That's multipath. We're going to talk back into multipath coming up later too. Okay? That's how we can get RF to bounce. And it happens on hard surfaces, typically water bodies, parking lots, hard packed soil. It doesn't typically happen in like grass or sage or trees or things like that that would absorb and not reflect the power. Does a really good job in one of these buildings that's made out of brick. Okay. So the start of this is our antenna. So far, so good. It's a very simple topic. But yet, electrical engineers spend lifetimes trying to figure out ways to make it sound really difficult. It's just a piece of wire. Every one of these that you take apart, you're going to find just a piece of wire. It's very disappointing when you take them apart. So we set up a piece of wire, and here's where the magic comes in. Power can't be created nor destroyed, only converted. Here's where the magic comes in. There's ohms, which is resistance. Everybody knows what ohms is, resistance? There's impedance, and there's ZO, surge impedance. So impedance, do you know the difference between ohms and impedance? Resistance and impedance. Anybody? It's easy. Resistance is a DC measurement. Impedance is an AC measurement. Everybody understand the difference between the two? Okay. So, impedance is affected by the frequency in which we use. That's why when you look at the specs on like your LMR 400, you look at your loss across LMR 400, and it's higher at 5.8 gigahertz than it is at 2.4 gigahertz. Because the impedance of the cable is different at different frequencies. Does that make sense? What we want to do though, because our transmitters, they have 50 ohm surge impedance for their output. That's how they're designed. So what we want to do is we want to make sure that we connect up a cable that has 50 ohms, because maximum transfer of power occurs at perfectly matched impedance. Okay. We can go through all the calculations, but that's not that much fun. I think it's pretty cool, but everybody goes to sleep. So we'll skip over to, you're just going to have to go with, this is true. If you suffer from insomnia later on, you can call me. I'll go through the formulas and I can prove it all out. What we're going to do here is we're going to take this transmission and we're going to bring it out. Now what we're going to bring it out to is a very specific length. If you look at the size of this antenna, this is for 900 meg. 900 meg is a much lower frequency than 5.8 gigahertz. Roger, don't correct me if this is a 2.4 one, just go along with me, all right? And the reason that is because there's a length of frequency. It's called lambda or wavelength. It's a very simple thing to think about on lambda or wavelength. everybody understands that AC, or alternating current, looks something like this. Would we agree? Okay. So, and I'm going to tie all these pieces together. There's a bunch of moving parts. They're going to come together. Promise. I got this thing I bent out. Look at this. This guy is open. He has infinite impedance out here. As I just took the transmission line and pulled it open. Some of you have probably seen antennas like that. We call them Cobra heads. They were really cool Cobra heads. Some people in this room are chronologically challenged enough to have, remember, TVs that you actually had to have rabbit ears on there. You know, there wasn't a cable that came in to a DVR. I'm just saying, some people, you know. So, these things come out, they have open impedance. That means there's nowhere for the power to transfer. Does that make sense? If power can't be created nor destroyed, only converted, and the power comes out of our transmitter, comes down our transmission line because we match the impedance right here, and right here at what's called the feed point, we match this to say 50 ohms also. Then the power comes down here. It hits this open and it cannot go anywhere. So that means that it reflects back. That might be kind of magic, but that's what it does. It reflects back. It's called reflected power. Well, it reflects back, and this guy's a perfectly matched impedance right here, 50 ohms, so he can't go back down the transmission line. Now he's stuck on this piece of wire, and the next alternating current is coming there also, pushing or boiling that wave off of that wire. So now it all turns into this, because he's trying to come back, the next one's coming down, pushes him off, and it boils it off into electromagnetic energy. That's all an antenna does. 4 years of school, that's all an antenna does. Holy moly, man. They got their money's worth out of an antenna, didn't they? Okay? So, that's all it does. Here's the cool part off of it. If I say that my AC is operating at 60 hertz, 60 hertz, right? That means it's 60 cycles per second. Everybody's agreeance on that too, right? Because Mr. Hertz, who was one of the leaders in AC and RF energy, they renamed cycles per second to hertz. So that means that every second, this thing alternates from being here to here. Does this 60 times a second, 60 cycles per second. Agreed? This is where it's going to become important. Once it comes off of here, it's electromagnetic energy. Electromagnetic energy is the same as light. That means it moves at the speed of light. The speed of light is 186,400 miles per second. Or 300 times 10 to the 6th meters per second. Okay? That's a speed, right? It's a constant. It's a constant speed. So, if it comes off of here, moving at this speed, and let's say that I was running at 1 cycle per second. We don't have something that low, but let's say we're running at 1 cycle per second. That means that it would go here, and it would restart itself again in 1 second, wouldn't it? And that means that in the amount of time when this thing's going, this thing would travel 186,400 miles away from the antenna before it started up again, repeating itself. That's wavelength. That's the length of the wave. Engineers are not real creative. They name things for what they actually are. That's the length of the wave. So if he was operating at 2 hertz, it would be half of this, wouldn't it? If he was operating at 10 hertz, he would be 18,640 miles away from it. If he was operating at 100 hertz, he would be 1,840 miles away from the antenna when he restarted again. Do you see this relationship? As I increase my frequency, the wavelength is getting smaller and smaller and smaller. Okay? So that's an important part. Wavelength gets smaller, frequency goes up, wavelength gets smaller. And you can even prove it because lambda equals constant divided by frequency. This is our constant and whatever frequency. And you can see, as this number goes up, this number has to go down, right? Higher the frequency, smaller the wavelength. You say, okay, well, cool. Why would you even bring that up? Because this critter right here needs to be 1/2 lambda. That's why when we get to be a higher frequency, we have a smaller antenna. If you look at some of your two-way radio repeater antennas, they're pretty big, 450 megahertz, as compared to 2.4 gigahertz, 5.8 gigahertz. Okay? That makes sense? If we're going to look at 2.4 gigahertz, the lambda off of it is about 4.91 inches. That's a wavelength off of it. Okay? You might double check that. That number might be wrong because I'm old. My mind is feeble. Okay? But it's around there. Okay? So, have I lost anybody yet? So cool. So now we have an antenna. It boils off energy and sends it out in a direction. So then what we do off of that, and then we have to worry about a couple other things. It takes a tremendous amount of energy to get that RF energy to boil off of the antenna. So getting it into free space causes a significant loss. So we have an antenna. He's hooked up to some kind of transmitter. He sends energy over here to an antenna, to some kind of receiver. Maybe we're playing some kind of cool music over here, okay? And over here, this guy is like, you know, a microphone with George over here. He's a very big mouth guy. So the idea is that the big mouth George talks into here. We take his voice frequency, which is around 300 to 1,000 hertz, and then we want to modulate it. To modulate means to change in frequency. Okay? We also have another word called heterodyne. Heterodyne means to mix or to change in frequency. And so we would move it up into frequency, put it to whatever frequency, you know, 452 megahertz, and send it across there. When we get it back over here, for the big-eared guy, it's got to be back into that audible range, right? The audio range is somewhere around 300 hertz to 3,000 hertz. Voice is concentrated around the 300, around the lower range. So we've got to convert it back down. We've got to demodulate it. Does that make sense? So as it comes out of here, there must be a significant enough power or voltage, or amplitude, or magnitude, or whatever other word we could come up with, that by the time it reaches this antenna, that it's still large enough for this receiver to deliver fidelity, faithful reproduction, fidelity. Okay? Does that make sense? We call this receiver sensitivity. Receiver sensitivity. What is your receiver sensitivity? Well, my receiver sensitivity is minus 82 dBm. We'll get to what dBm is in. In other words, what it's saying is that my power must be at minus 82 dBm, whatever that might be, for me to get a faithful reproduction of what the big mouth guy said. Make sense? So that's it in a nutshell on the antennas. Now let's bring the... But not yet, we got more antennas. More antennas, not yet. So that's the nutshell of the antennas. Now the next thing is, how do we go from this ugly little thing to this ugly little thing, or this ugly little thing? How do we pick ones out? I mean, that's the big key, right? So how do we decide on our systems how we can, you know, come up with an antenna? Well, the easy answer is there's an approved antenna list, so you got to go off of that. But off of that, we also then, you know, say, well, let's come up with some other antennas, or let's see what else for our use. So we have an omni antenna. Here's some of the crux in life, and here's some of the reason that in an open pit environment, you would design a network such as this. In a metropolitan area network, you would have light poles and you would have access points on top of the light poles. They would radiate off of this. You'd have other light poles, and they'd radiate off of this. You could easily mount these APs with these guys like this, and mount them with a little mounting bracket like this up on top of the light pole. You wouldn't get any radiation or very little right at the bottom of the light pole, but most people don't hang out at light poles with their laptops. Most, maybe some do, I don't know. Okay? But you would be able to throw this down the streets then that way, right? Because this would be creating those donuts, those bagels going down the streets. Okay? However, in an open pit environment, unlike a metropolitan deployment, you have a hole in the middle of your world that's about a mile deep. There are no cities out there that are designed with a hole a mile deep. This introduces some extreme issues. The first issue is, this is a beautiful drawing, by the way. I don't care what you say, it's a beautiful drawing. This is exactly how an open pit looks. Okay? Every one of my shelves right here is exactly the same. Your eyes may be off, maybe. So I have a haul truck right here, and I have an access point up here on the rim, which is the design criteria, and we'll go over why that's a good design criteria. And I put a nice antenna on here, so he's got a radiation pattern like this. He's got a great throw, he goes a long distance. What's the problem? He can't see down there, can he? He can't see down there. And much like a flashlight, because remember we talked about the flashlight, if I stood up on the top of the flashlight, you're probably able to see light up there, but not very good, right? So maybe you pick up a signal at minus 92 dBm, whatever that might be. It's very low though, right? Very low. So we could come up with another solution, which is what you would do if you didn't have a choice of antennas. You would take this antenna and tilt it like this, which would then give you some coverage down into your open pit, but not a lot, right? And it would also cover any helicopters that you wanted to talk to that were flying around up there, which is a waste of energy. So what you would do then is you would take a reflector and put it back here. Take all of this energy that you wasted here and try to send it out this direction with a wide beam. So a nice wide beam, meaning that the wider the beam, the less energy I have focused in one particular direction. Okay? Remember the same as if we were out in the field and you put an incandescent light bulb and you're standing 10 feet away from it and you look at the light bulb, it's kind of bright. You put it into a reflector behind it into a floodlight and shine it right into somebody's eyes, they get the dots for free. Okay? Same amount of energy. Same amount of energy. So what we try to do here is come from the rim down this way. And then the other thing is that on the haul trucks or the mobile fleet, we try to put a very, very low gain omni. So if we have omni choices, here's an omni that's, let's say, 3 dBi. We'll get into what that might be. His donut looks something like this. That's a perfect drawing. And this is a donut, right? So he rotates 360 degrees, right? He looks like, is there a bagel back there? Are they all 8? All right. Hang on, George. Be all right. There'll be a bagel coming up. Oh, there's a perfect one, too. Look at that. This is a perfect antenna bagel. So it looks like this all the way around. This is where the antenna's at. So it goes around. Okay? And then as I go ahead and increase this power to maybe 7 dBi, my antenna now looks like this. Same amount of energy, right? Because power can't be created nor destroyed. What I did is I squished it down to make it more like a flat bagel now. And if I went to, like, say, 13 dBi, now I have, like, a tortilla. Well, this is actually going to go over here, right? I mean, it goes a long way, but only if you're on the same plane with it. So on the mobile fleet, we put this guy on there. Man, he's going to do awesome talking to that high wall over there if he could, anything to talk to. That's why we put big, fat bagel antennas onto the haul trucks. We put 3 dBi. They don't have great throw. They don't have great distance. That's why we have to have more trailers. If we were flat and on the same plane, we could put higher directional antennas on them, and we could get less trailers. We don't have that option because we dug a hole in the ground. Okay? So does this part make sense on why we selected these types of antennas? So you could then say, without even knowing what dBi is other than its gain, and I'm going to go over that because George wants to keep it as a separate topic. So you could say that the higher the dB, the higher the gain, the more directional an antenna is. The more directional it is. That's a very, very easy statement. If you had a choice between a 3 dBi antenna and a 23 dBi antenna, you could say that the 23 dBi antenna is much more directional. If you chose like a 45 or a 60 dBi antenna, it's like a laser. That's how the energy is concentrated. So what does that mean? That means that it's probably a super duper choice to put on a stacker that's going to vibrate like this. And you're going to try to hold it to the other end to try to point down there to talk to the other end like this. Right? What do you want? You want a big fat one that's not going to go a long distance, maybe a mile. Stackers go about a mile and a half. And you want to be able to talk to the other side, right? You want the E-house to talk to the stacker. And so you need a big fat one. You put a super gain one on there. And this is where most wireless mistakes are made. Because most wireless is designed that more is better. I need more power. I need a higher directional antenna. I need it to be focused. I need energy, because strength has got to be the best way. It's so wrong. Most of the time, less is the way to go. Now here's the next thing that we look at. An antenna itself has retroprocessity. It means that it can transmit or receive. That's one of those super duper college words. Man, they're so cool. Okay? So it means that it does both transmit and receive. There are not transmit antennas and receive antennas. There are only antennas because they're only a piece of wire. So if an antenna is a 13 dBi, meaning that it has 13 decibels of gain, whatever that means, it means that it has 13 decibels of gain if it's transmitting energy. It also has 13 decibels of gain if it's receiving energy. Does that make sense? Antennas. Piece of cake. 3 major types. Omni antennas, sectorized antennas, and point-to-point antennas. So we use all 3 in different locations. We use omni antennas when we want a big throw, but we don't know what's going on. We use sector antennas because why would we waste energy back over here where we have no communication? It makes no sense to waste energy back over there. Same reason that when you see light poles in communities now that are trying to control light pollution, you see that they have great reflectors on the top so that they don't just throw light up into the sky. They have it so it focuses it down onto the ground so they're not wasting that energy. It's a huge savings in energy. And then we have very narrow antennas so that we can have a very, very focused beam coming out of the antenna. And we use that for a point-to-point so that you can go from this point to that point over there. We know that's where it's going to go. It's going to stay in that point, and we want to get a nice, strong antenna. Once again, remember what we talked about earlier is that wireless is an extension of your infrastructure. And almost all wireless is designed to be layer 2 transparent. So it's the same as if I drug a piece of cable, a Cat5 cable, out to the haul truck and plugged it in. It's the same as if I drug fiber over to the container and plugged it in over there. The idea is to extend your infrastructure. Okay. All right. That's antennas, nice and easy. They're pretty boring. Now let's get into some calculations.